Okay, so we can conclude the day with the final lecture, but so not the final, but the third lecture of Mathew, and I spoke a lot of the fourth moment of Dirichlet function. I don't know if you will cover this, but if so, that would be great. Go on.
Okay. Yeah, thanks. Yeah, that's good to know because I don't always know what everyone else is doing during these lectures. So let's share my screen on my tablet. Okay. So last time I talked a little bit about the second moment of Dirichlet L functions and also left it as an exercise to compute the first moment asymptotically. And from this, we deduced a non-vanishing result from these moments. And so that's what's on the screen right now. So let's start a new new page for Wednesday. So okay. So for a lot of our applications of moments, what we do is we often study modified moments, so moments that are modified in some way. So typically what this means is that we're going to multiply by some kind of Dirichlet polynomial. Okay, let me write what I'm saying. So applications use a modified moment. Such as so for the example of Dirichlet functions, let's look at like the second moment, but then we're going to multiply by some sort of extra sum with some coefficients. So we're going to multiply by a sum over L, let's say, with some coefficients A sub L times chi of L. So this is a modified moment, and so this and then this. Okay, so this is a Dirichlet this is a finite Dirichlet polynomial. And there's a tremendous amount of work on these sorts of things and trying to make good choices of this Dirichlet polynomial in order to extract useful information from these kinds of modified moments. And I want to talk about some of the different choices that have been made and what they do and what they're good for. But let me just first say, so if you just square out this Dirichlet polynomial, you can think of this as a sum over L1 and L2 up to some bound. So you should think of L as some power of P, like P to the delta. And often delta will be fairly small. Okay, so we'll have A sub L1, A sub L2 complex conjugate. And then we'll have what we might call the twisted second moment of Dirichlet L function. So we'll have L of a half chi squared times chi of L1 chi bar of L2. And so this inner sum over chi, I would call that a twisted second moment. Okay, so it's the second moment where we've multiplied by some values of these Dirichlet characters. Okay, so what's a good choice? So one interesting choice goes under the name of Mallesham. So in this case, we would choose. Okay, and let's give this a name. This Dirichlet polynomial, let's call it A of chi. So we want to choose A of chi, and then we have to really use our imagination here with a squiggly approximation sign to think of this as the reciprocal of the L function at a half. I'll just put like some quotes around here to really signify that this is pretty hand wavy. But so we want to think of it, but we want to think of it as somehow some kind of approximation to the reciprocal of the L function. More precisely, what we really do is that we'll pick we might choose something like A of chi to be sum L up to capital L. So we'll take the Mobius function of L times chi of L over, let's say, square root of L, and then there's some kind of smoothing factor, so it's log of capital L over little l. So okay, so this is a pretty common choice for a mollifier. So this is okay. So just to say, so if you look at the reciprocal of the L function, maybe off to the right of the critical strip where this thing converges absolutely, this has the Euler product, 1 minus chi of p over p to the s. And then if you just multiply this out, this has a Dirichlet series Mobius function of L, chi of L over L to the s. And this really only converges for real part of s bigger than 1. But we might sort of hope that it's like if we take a partial sum of this Dirichlet series, that it's not too far off from some kind of approximation to the reciprocal. Yeah, and it actually works. There is an important feature, which is this this log of capital L over little l. This is some kind of a smoothing factor. So if little l is pretty small, this is size of like little l is 1, then this is like log of capital L. But the closer little l gets to capital L, the smaller this weight function becomes. In particular, when little l equals capital L, this is log of 1, which is 0. So it does sort of decay at the endpoint there. And I think Selberg might have been the first to notice this, but that you want to use this smoothing factor. And so, okay, so maybe I don't want to go into all the details of this. This would be, this would fill up the entire lecture, but there's a nice paper by Ivanians and Sarnak. I forget the title now, but they actually work all these things out. So they work with this mollifier. They work with more general coefficients, and they do some kind of optimization at the end, and it turns out it's basically the one that I just wrote down. Right, and so then they have. So I'll state their theorem. I'll just state it as a proposition, since I'm not really proving it. So first, if you sum over chi mod p, and you take the second moment of this L function squared times this Dirichlet polynomial, this mollifier squared. This is asymptotic to some constant depending on delta times p, where L is p to the delta. And so basically this saves a log p. Okay, that's the whole point. So there's no log p here. I don't know if this is clear what I'm trying to say. Like if you don't have the mollifier there, if you just had the second moment of Dirichlet functions, then we got p log p. This is what we already mentioned yesterday. But the whole problem is, how do you get rid of this log? And so that's what this mollifier accomplishes. And then the second result, which is much easier, and it's just a little bit harder than the exercise I assigned you yesterday, which is to compute the first moment of this, and then this will also be asymptotic to p. So in this case, both the first and second moment have the same order of magnitude. They're both like p. And then so using the exact same argument that I gave yesterday, about the non-vanishing, counting the number of chi's that where the L function does not vanish, this will imply that n of p now is bigger than p. So this is a positive percentage. And the implied constant depends on delta. So if delta is small, you get a small positive percentage. And the larger you can pick delta, the better positive percentage you'll get. So for the details, you should look at the paper of Ivanians and Sarnak. And there are lots of other papers that look at mollified moments. There is I would say, okay, so there's some nice works on this about there's the so-called ratios conjecture. Of I guess Conry Farmer. Okay, I can't remember all the author. Okay, I think so there's the integral moments conjecture, that's CFKRS. That's the easy one for me to remember. And then there's the ratios conjecture, and I think Zernbauer is a part of it, and I don't remember who all the authors are, so I apologize about that. So the ratios conjecture builds on the integral moments conjecture, and it can be used to sort of predict what these asymptotics are, which is actually rather difficult. If you go through the actual proof, like in Ivanians and Sarnak, you go through this whole complicated analysis of all the main terms, and then when the dust finally settles, you get this constant depending on delta times p. And there's this ratios conjecture that lets you guess the answer much more quickly, and then having the answer predicted ahead of time makes it a lot easier for proving anything, and you can then have something to check against. And it also helps you, like if you want to try some new kind of mollifier, you might plug it into the ratios conjecture and see what you get and see if it's useful. And if your new idea of a mollifier turns out to not be very useful, like it doesn't work or it doesn't really give you what you hoped for, then you might not bother like working out all the details. So it's a much more efficient way to tell if this is good. So so the ratios conjecture was sort of developed in this paper, whose complete list of authors I'm having trouble remembering, but there's a paper of Conry and Snaith, which I think is called Applications of the Ratios Conjecture. That's the paper that you want to look at. So something about applications is in the title, and I'm just telling you how you Google. So Google Conry Snaith applications of ratios conjecture or something like that. The paper will come up, and they'll do lots of examples like this. And yeah, and so this is I think this is a good way to think about mollifiers because it's actually quite complicated to try to carry this out in any given instance, and it's very easy to make mistakes. And so this is a kind of a reliable way to predict the answer. So I'll just make a little plug for that. Another thing to say, so like what's this mollifier actually doing? So it's not actually the reciprocal of your L function. Like your L function, first of all, could vanish. And then if it was the reciprocal of your L function, this would be infinity. And then, we don't want to, or we'd be dividing by 0, and we don't like that, obviously. I don't have to tell you that. So what it's supposed to be doing is it's supposed to be at least dampening the large values or mollifying the large values of the L function. So if the L function is big, the mollifier is supposed to be somewhat small to compensate for that. So that's why you save the log p when you do the second moment here. And one thing that it does, so maybe how do I get at this? So if you recall, when we did the second moment, we had the main term sort of looked like we had a P from just counting characters, and then we had a sum over L, and it was 1 over L, and then we had like some weight function. Maybe L went up to root P or something like that, and that's not very important, but you want to think of this as like a sum L up to root P, or some power P, 1 over L, and this is like a partial sum of the harmonic series, and that's where so the log came from. So the log P came from the harmonic series. So this is asymptotic to log of x, which, okay, if you can get from the integral test from calculus. So, okay, so here's the observation. So what if you had like a partial sum? Or okay, let's write it like this. So what if we had a sum over L between y and x? Okay. Oh, so maybe I'll fix this. So the sum is equal to log of x plus big O of 1. And the big O of 1 you can quantify as well. You can get lower order terms here. So if you do this, oh, maybe I'll make this one-sided just to be cute. So this is the same as the sum L up to x, 1 over L minus the sum L up to y, 1 over L. And so this is log of x minus log of y plus big O of 1, which is the same as log of x over y plus big O of 1. So if what do I want to say? So if y is like I don't know, like x to the delta, then log of x over y is log of is this what I want? I don't think this is what I want. Maybe I do. Right, so this is log of x to the 1 minus delta, which is 1 minus delta log of x. Okay, I think I changed my mind. Okay, I was diverging from my notes here, and I think I don't think this is what I want to mention. Yeah, what am I trying to say? Okay, yeah, I changed my mind. All right, let's let's just ignore this discussion altogether. Yeah. One thing you learn when you teach is that you have to cut your losses sometimes. If you just sort of do something a little bit wacky, then you just have to stop and not go down that rabbit hole. So okay, I'm gonna stop whatever I was headed towards and move on. So that's my very, very brief discussion of Mallefires. And yeah, and so look at these other, like look at this paper by Connery and Snaith for applications of ratios. You can find lots of discussion on Mallefires. I mean, it's kind of Mallefires are kind of more of an art than the science. Like we don't really always know like what's like the best choice of mollifier. Like people come up with new types of mollifiers and you get better results for some questions and you know, we don't really know what we're doing. It's kind of a uncharted territory in some ways. So okay, so that's the mollifier method. I wanted to mention there's this beautiful result. It's really a method. I would call it a lower bound method. Rudnick and Sarnak, or Rudnick and Sundararajan. There's various papers of Rudnick and Sarnak, so it just sort of rolls off the tongue. But no, this paper is by Rudnick and Sundararajan, and I want to explain what this is because it's the idea is very simple to explain, and it gives you quite strong results. And so so there's a conjecture. So I guess I've mainly been focusing on moments of Dirichlet L functions for this lecture series so far. So let's stick with that. So there's a conjecture that I sort of alluded to, which is that if you take the 2kth moment, and let's just take prime modulus. So there's a conjecture that this is asymptotic to some constant depending on k times p, or maybe p minus 1, but it doesn't really matter, times log, p minus 1 is the number of Dirichlet characters. Maybe we should take p minus 2. That would be the number of primitive Dirichlet characters. Anyway, it's basically p and then log p to the k squared. So for example, just to check, if k is 1, that's our second moment, and you get log of p here, p log p. And so this is a conjecture. This is sort of, I guess, a folklore conjecture for some period of time that there should be some kind of asymptotic like this. And then, but this is part of the whole random matrix theory. I guess approach to getting conjectures about various quantities, statistical quantities about L functions. So at this point now, there's an integral moments conjecture of Conry, Farmer, Keating, Rubinstein, and Snaith, where they get C sub k is equal to like completely known, and you get a full polynomial in log p main term. So so in fact, it's not just log p to the k squared, it's a polynomial of degree k squared in log of p, and then they conjecture some power-saving error term. So this is a conjecture. You can guess the size of this. So guess shape of the, maybe this is just like the first comment. So you can guess the shape of the answer by looking at the diagonal. So what do I mean by that? So if you just sort of look at chi mod p, and then so the kth moment should be something like sum over m dk of m. That means the k-fold divisor function over square root of m times chi of m. So that's like your L function to the kth power. And then you do the same thing with chi bar of n over square root of n. And then there should be some kind of approximate functional equation that tells us that m and n go up to some power of p. And for this discussion, it's not going to matter too much because we're just trying to get the order of magnitude. So v of mn, and then this goes up to p to some power, p to the, okay. It doesn't matter. I'll just put a little question mark there. It's irrelevant for this discussion. And so now when you sum over chi mod p, you get this congruence, and then you just select the diagonal. So the diagonal is exactly p, or p minus 1, times sum over n. So you get dk of n, quantity squared, over n, and then n, v of n squared over p to whatever power it is. And you can do a little calculation and check that okay. So this should be something like, if you take the definition of this v function as an integral, so this should be like p to whatever power, p to the question mark power to the s, yeah, and then you've got like your g of s over s, you've got various gamma factors that don't matter, and then you've got the sum from 1 to infinity, dk of n squared over n to the s, ds, and you mainly just want to know what's the size of this, of the pole. like what's the order of the pole here? And so this sum over n, this has an infinite product. That's an Euler product. It's a multiplicative function. And then at primes, so at a prime, whoops, 1 over, so the coefficient of 1 over p to the s will be the k-fold divisor function of p quantity squared. So the number of ways to write a prime as a product of k numbers is k, I guess. All but one of them are factors are 1, and the other one is p. So you'll get k squared here. And then there's coefficients of p to the 2s and so on. And so this thing behaves like zeta of s to the k squared power. So you get a pole of order, oh, and it's at 1 plus s, right? Because I forgot the 1. And then, okay, so it's 1, oops, p to the 1 plus s, 2 plus 2s, and so this should be zeta of 1 plus s down here. So this has a order k squared pole. And then from the g of s over s, you get 1 extra pole. So in total, you get k squared plus 1 poles. And then, so that means that basically in this p to the power s thing, the p to the, just imagine p to the million to the power s. When you take the Laurent expansion of that thing around s equals 0, you'll get, that sort of tells you how many terms you can take in the power series expansion. And so, this tells you that this is like p times log of p to the k squared power. So all you have to do is just look at the diagonal term and say like, okay, the diagonal term is giving you something of this size. And then, to get the order of magnitude of the moments, you might just say, okay, all the off diagonal terms give you a main term that's at most the same size as the diagonal term. So that's just the guess. And it seems to be the right answer. And Rudnick and Rudnick and Sundararajan proved unconditionally in many, many situations that you can get a lower bound of this order of magnitude. So, so this is a theorem of Rudnick and Sundararajan. It's a very flexible method. And so the theorem is that if you sum over chi mod p, L of a half chi to the 2k, that's bounded from below by some constant depending on k, p, and then log p to the k squared. And this is for positive integer values of k. So k is 1, 2, 3, etc. So it's a lower bound of the correct order of magnitude for the moment. Okay, and this is unconditional. And so one nice thing about this is it shows that these Dirichlet L functions do take, reasonably large values at some rate because the moments are consistent with this. So this is proving like existence of fairly large values of the Dirichlet L functions, like quite often. Maybe I won't make that precise, but you can just see like, okay, it can't always be that the Dirichlet L functions are bounded by like log of p or log of p squared or log of p cubed or anything like that, because if it was any fixed power of log of p, then you wouldn't get log of p to the k squared. It'd be linear in k in the exponent, but it's quadratic in the exponent. So anyway, so that's nice. So here's the idea. So the idea is very simple, and it's a Cauchy-Schwarz argument, and it's assuming that we can get so the basic input is that that we can understand the second moment and a little bit more. So we can get an asymptotic for sum over chi mod p Dirichlet L function squared times like your A of chi squared for L equals P to the delta sum fixed delta positive, but arbitrarily small. So, okay. So I can't prove this. I mean, I can't prove the asymptotic for you or I could, but I'm not going to because it would just take too much time and well, you know, that's the only reason. It's just the time considerations. But we did the case the other day where we had the second moment of the Dirichlet functions without this extra Dirichlet polynomial, and we proved, if you remember, we proved like p log p and then some error term like p to the 3/4 or something like, or maybe it was p to the half. So we got a really good power saving error term. And so you can just imagine like now just do the same thing, but now you've got a little extra chi of L1 and a chi bar of L2. That's going to make the problem a little bit harder, but it should be sort of continuous in terms of L1 and L2. And that's sort of the heuristic, like to kind of convince yourself that something like that should work. So you should still be able to get an asymptotic for this as long as L is pretty small. So that's our basic input, is that we can do that. So now what? So I want to let A of chi be sort of like A1 of chi to the k minus 1 power, where A1 of chi is a sum over L up to some bound. I don't know, let's call it L1 or something. Chi of L1 over square root of L1. So A1 of chi is kind of like a short version of L of a half chi. Like imagine that it's kind of like the L function. It's a short partial sum of the Dirichlet series for your L function. It's not really close to L of a half chi, like in like a pointwise sense or anything like that, but it's maybe just in your imagination, think of it as like kind of like an approximation to L of a half chi. And then when you take the k minus 1th power of it, then it's, you know, A of chi is kind of like, so it's just, you take the kth power of it, this is the sum L up to, well, it's a sum over all the variables up to k, so, or L1 up to L sub k, each of them goes up to L1, chi of L1 up through LK over square root of L1 up to LK. And this is kind of like your, you know, again, in like scare quotes, L of a half chi to the kth power. And this thing is some sort of Dirichlet polynomial where it goes up to some, certainly all the coefficients, the biggest the coefficient ever gets is L1 to the power k. And then, yeah, and then the coefficient here is kind of a divisor function. It's some sort of restricted divisor function, but where all of the divisors are at most capital L1. But anyway, so this is some kind of Dirichlet polynomial that if you really stretch your imagination, you might think of as like it's a short approximation to L of a half chi to the k. Actually, I guess it should be k minus 1. Oops, I got the indexing wrong. But that's okay. Sorry, it's kind of hard to see it. I know. The reason it's k minus 1 is because I already have the Dirichlet L function there, like appearing, and then I want like the sort of a k minus 1th power. So when I put them together, it's like the kth power. So this is supposed to be kind of like the 2kth moment of Dirichlet L functions. I mean, it's not really that, but we hope it's like that. Okay, so now let's look at this. So we've got our sum over chi mod p. we've got our L function squared. And then we've got our sum over these coefficients. So it's L up to L1, chi of L over root L. And then this is really to the 2kth power. Sorry, 2k minus 1th power. Okay. And then now I want to use Holder's inequality on this. Okay, and so I want to get the 2kth power here. So that means I'm going to raise the first one to the kth power, and then I'll have a 1 over k power here. And then the other one is we'll have the dual exponent. So this is like that was my a1 of chi. So I'm going to have a1 of chi to the, or it's a1 of chi to the k minus 1th power. Okay, let's see. So the other one, okay, so right, in Holder's inequality, you've got the sum of the reciprocals of the exponents is 1. So I want one of these to be k. And so that means 1 over q is 1 minus 1 over k. So that's k minus 1 over k. So that means q is k over k minus 1. So I'm going to take this thing. Okay, so I've got my a1 of chi to the k minus 1th power. Then I'm going to raise it to the k over k minus 1. Take that to the k minus 1. Um, 2kth moment to the 1 over k power. And then we've got our modified thing. So this is this a1 of chi to the 2k raised to the k minus 1 over k. Okay, so now, so this is this first thing is the true 2kth moment. That's our actual 2kth moment of the Dirichlet L functions. The thing that we start with, maybe I'll just write it in green, like by assumption, so we can assume we have asymptotic here on this first product, because that was our basic input, is that we can handle the second moment of Dirichlet L functions times a short Dirichlet polynomial. And L1 is going to be some very tiny power of p, fixed but tiny power of p, so that this fits into our basic input of what we can handle. Similarly, this we can also handle by assumption, because it's actually even easier than the Dirichlet L function. So the same method that handles the Dirichlet L function times the short Dirichlet polynomial lets you just handle a short Dirichlet polynomial all by itself. And then both moments, or both expressions in green that we can handle, have the same order of magnitude. And okay, and so then if you just rearrange and solve for the true 2kth moment, we get a lower bound on the true 2kth moment, and then you just do the calculation. Everything has the same order of magnitude, and so you still get the same order of magnitude for the true 2kth moment. So if you want to see more details, there's this short paper of Rudnick and Sarnak. Or Sundararajan, I keep saying that. There's this QUE conjecture of Rudnick and Sarnak. I talk about it all the time at different times, so it just really comes all the time. So Rudnick and Sundararajan, and they and so they explain this in more details, but it's quite right? It's quite flexible and it works in great generality. And so whenever you can handle your second moment with a little bit more, so if you can handle the second moment with like a power saving, then that indicates you should be able to put on this extra Dirichlet polynomial, and you can then get you know, the asymptotic for that modified thing, and then that lets you get this lower bound on any moment you want. And then maybe I should also just briefly mention that there's also a method of Sundar-Rajan, famous result of Sundar-Rajan from around, I don't know, you know, around 2010, I want to say. But it's called Moments of the Riemann zeta function, I think. And so he shows that if you take the 2kth moment of zeta, or okay, since I'm talking about Dirichlet functions, let's state it for Dirichlet functions. Again, it's quite flexible. So if you sum over chi mod p, L of a half chi to the 2kth moment, he proved that this is bounded by p log of p to the k squared plus epsilon, assuming RH or on GRH. So you assume the generalized Riemann hypothesis for all these Dirichlet L functions, then you can get an upper bound that's not too far off from what we conjecture as the asymptotic, and also not far off from the lower bound that I just presented. So assuming GRH, we've really got the moments, like we pretty much have their order of magnitude. I don't want to go into the details of how this method works, but I just wanted to advertise it since we're talking about lower bounds, and also there's a later theorem of Adam Harper, which removed the epsilon. So in light of Harper's work, we really do have the same order of magnitude for the lower and upper bounds in the kth moment, 2kth moments of let's say the zeta function or Dirichlet functions. So that's quite some like really amazing progress on in this field in the last decade or so. All right, so we're still on the topic of modified moments. And so the next kind of modification I want to talk about is a very important notion of an amplifier. Again, I'm not sure if these have been discussed at all in any of the previous talks, but even if they have, I think it's okay to give another take at it. So here, the idea is we want to choose A of chi to be sort of big when chi, okay, maybe you first, maybe you pick a character psi mod p. So take your favorite Dirichlet character mod p, and then you want this Dirichlet polynomial, this A of chi, to be large when chi is equal to psi, and then you don't really care, or hopefully or maybe it's not too big for the other values of psi. So some kind of you're trying to amplify the contribution from that one character psi. So it's like turning up the volume, on that one character, like that one harmonic, and amplify the effect of that one character. So an example of something that might do this should be just choose A of chi to equal some little l up to capital L, chi of L, this is our chi of L times A sub L, and so you choose A sub L to be psi bar of L. So then A of psi is some little l up to capital L so it's psi of L times psi bar of L, which is basically L. The only times it's not 1 is if you hit an integer that's not coprime to P, and so that's quite rare. So basically it's L. So this amplifier has the size L when chi is psi, but for chi not equal to psi, A of chi then will be the sum little l up to capital L, chi times psi bar of L. And so this is now like a partial sum of these coefficients. And so maybe we should think of this as like square root of L. Now we don't actually know how to prove that, but the heuristic, the square root heuristic tells us that this should be around size square root of L, which is much smaller than L. So this should indeed give us something that is large when chi is equal to psi. So okay, so then how does this actually play out? So you might look at your sum over chi mod p, L of a half chi squared times this sum. And okay, how much do I want to say here? So again, you have this. So if we kind of go through what we did when we were trying to get this the bound on the Dirichlet L functions, the second moment, it's very similar, except we have these extra weights. So we'll have our chi of L1, chi bar of L2, and then so this is just maybe approximately. So what we did when we estimated the second moment was we wrote it the L function basically as chi of m chi bar of n over square root of mn with some weight function v of mn over p. Up to like a factor of 2. We're only looking for an upper bound, so factors of 2 I don't really care about. But actually, I mean, I think I can make it precise and just say this is equal to twice this. So see yesterday. Okay. So excuse me. So you always have to perform your averaging over your family. So here the averaging over your family is using the orthogonality of characters. So let's just see what happens if we do that. So we have a sum over m and n now. So we're going to get okay, 1 over square root of mn from that. And then so the congruence condition that we're going to get is that m times L1 is congruent to n times L2 mod p. And then v of mn over p, basically. Oh, and then essentially a p, or p minus 1. It doesn't matter. Okay, so now let's look at the diagonal. That's where m L1 is equal to n L2. It's convenient to for fun or for simplicity. Let's suppose a sub L is supported on primes. So the density of primes is like 1 over log. You don't lose very much. We might lose a log or something, but we don't really care about that very much for this application. And so just for simplicity, let's assume that it's supported on primes. That's going to make this easier. So if L1 and L2 are primes, then okay, I guess there's 2 options. So option 1 is that L1 equals L2. So then if L1 equals L2, that implies that m equals n. And then the other option is that L1 is not equal to L2. And then that implies that L1 divides N, L2 divides M. And in fact, we can write N equals L1 times, I don't know, K. And M will also be L2 times K. It's the same K. So just from solving this equation, the diagonal equation. So the option 1 terms gives rise to 2 times P. You've got a sum over L, like let's say L1 and L2, let's just call that L. So we'll have A sub L absolute value squared. M and N are the same, so we've got a sum over M. Now it's 1 over M, V of M squared over P. And so this will be basically 2P log of P times this sum of squares of these coefficients. So, so this is approximately like P times L. If we just choose AL to be the primes up to capital L. So as an order of magnitude, it's P times L. But the option 2 terms are also pretty similar. They're actually, I think, slightly smaller, but whatever. So we can just do this. So from option 2, we'll get 2 times P. We'll get a sum over L1 not equal to L2, AL1, AL2, and then sum over K. Right, so M is, yeah, so square root of L1, L2, 1 over K. V of L1, L2, K squared over P. And just the sum over K, just think of that as another log. So this is like 2P, and then it's like log P, and then it's like a sum over L, 1 over AL over root L, quantity squared. So this is like 2P log P. So this should be like square root of L over log of L, quantity squared. And so this is actually slightly smaller. So this is like P over, or P times L over log of L. So anyway, so these option 2 kind of diagonal terms are slightly smaller than the option 1 diagonal terms, but never mind. The whole point is we get basically P times L from the diagonal. Okay, so that's good. And so it's a very important point that this only grows linearly in L. Okay, so this is an important point. The diagonal only grows linearly in L. But the when chi is equal to, but for comparison, when chi is equal to psi, then we said A of chi is like, well, so we're squaring it. So this is like L squared, and this is quadratic. So, so the fact that these are growing at different rates is something that we can leverage. It means that the diagonal term lets like we kind of yeah, the diagonal term is sort of good in terms of what happens when chi is equal to psi. So okay, so maybe I'll just write a little bit about what happens with the off diagonals. It would really be, again, like a little more involved to do the whole thing. But from the terms where M1, L1 is not equal to M2, L2, what do we get? So we're going to get our P out front, or 2 times P. Again, it doesn't really matter. We've got our sum over L1 and L2. We've got our AL1, AL2 bar. And then they're still congruent mod P, but they're not equal. We've got our weight function. I guess for some reason I started labeling these M1 and M2. I guess M became M1 and N became M2 for some reason. I don't know. doesn't really matter again, and then over square root of M1, M2. So then we might say, let's say M1, L1 is equal to M2, L2 plus P times K, and let's just say K is positive. It's pretty symmetric. So if it went the other way, you could just swap the roles of which one's M1 and L1 and which one's M2 and L2. It's symmetric between these two things. So then PK, you can solve for, like, this is congruent to negative M2 L2 mod L1, and you can eliminate M1. So everywhere you see an M1, you can solve for it with this equality. And then the condition, this congruence condition, then is you can interpret as a congruence condition mod L1. And so this should be good because this L should be fairly small. So this congruence should be smaller than P. So we now have a congruence that we're trying to solve that where the modulus is smaller than before. So P is a big number, but L1 it should be much smaller. So this is some progress, and so this is like maybe the key step, and then we can do various like Poisson summation. So you like maybe use Poisson summation in K, and additional moves after that. So if you want to actually see what can be done here, so there's a paper of well, there's a couple papers you might look at, but this is the problem that was studied in this paper by Friedlander and Ivanitz from 1992, and this is the paper that introduced the amplifier. So this is the first occurrence. How do you spell occurrence? Occurrence, is it E or A? Occurrence. Okay, whatever. First occurrence of an amplifier. And it's in a very short paper. It's in this Michigan math journal, and this was, it sort of slid under the radar. So it's this deceptively, I don't know, maybe it's kind of deceptive that this idea first occurs there, and then the idea then was used in many other papers. So then you might look at, there's a series of papers by Duke, Friedlander, and Ivanitz. I'm sure we've been seeing these initials DFI all over the place at this kind of a school with lots of delta methods and everything. So DFI series of papers for more amplifiers everywhere. But anyway, this is the first case, and so Friedlander and Ivanitz looked at this kind of amplified second moment of Dirichlet L functions. Their problem makes it a little bit difficult to try to get at the main idea, because for the second moment, basically you need a long amplifier. And I think it's better to just to try to explain the idea or explain what's going on. Maybe we should look at the fourth moment instead. Because the amplified fourth moment, you only need a short amplifier. And so by needing a long amplifier, basically they need to, like, so just imagine that their amplifier is already the L function, another copy of the L function times an amplifier. So they're really getting at the fourth moment in this indirect way. So long amplifier means like the same length as another copy of the L function times another amplifier. So just for for purposes of discussion, let's look at the fourth moment problem. So Philippe said that he talked about that a little bit. So that fits well with what I'm saying here. So let's look at the fourth moment. So look at the fourth power, and then I want to multiply by this amplifier. So, okay, and so what we should expect here, or hope to prove, is that this is bounded by P times L from the diagonal. So the fact that we're looking at a fourth moment, okay, maybe I'll change this to P to the 1 plus epsilon. So the fact that this is a fourth moment, what that does is it changes the the diagonal term involves divisor functions, and so it's like a power of log times larger. So it's just like when we were looking at the fourth moment of Dirichlet functions, or just general the 2kth moment, we had a higher power of log of p. So let's just sidestep that by putting in a p to the 1 plus epsilon. And then for the off diagonals, this is the part that I didn't really talk about what you do, but you can try to follow these moves that we mentioned earlier, and you sort of solve these congruences using maybe like a Poisson summation argument. And what should you get? So from the off diagonals, what you want is you want to save a power of p, but lose a power of L. So, or maybe I should use a different letter than delta, because delta was okay. So we want to assume that it has something of this form. So from the off diagonals, so alpha is some small but fixed positive quantity, and A is probably large. I mean, we'd like it small, but it's usually large, but it's also fixed. So, think of alpha as like 1 over 100 and A like 100. Okay. So great. So the A part, that part like might, or you might think of A as 2 or something. So we already know that like we need some kind of quadratic growth in L, because the one bad character is already growing quadratically in L, but that only happens for one character. And so that's consistent with this P to the 1 minus alpha times L to the A, because maybe like, P to the 1 minus alpha is sort of like the number of bad characters where it could be big. And then the diagonal is size P times L that grows linearly in L. So now, so this is what the shape that these amplified moments generally take. So you have a diagonal and you have an off diagonal. The diagonal grows linearly in L, and the off diagonal grows more than linearly in L, but you save a power of P. Okay, so this is the structure that we're looking for. So diagonal is linear in L, and off diagonal is you save a power of P, like in the P aspect, but you get a bigger power of L. So what is this good for? So what it's good for is you can say, okay, this moment is greater than or equal to our preferred character, which now we're raising it to the fourth power, times our amplifier evaluated at psi squared, and the amplifier is like L squared. So this, if you put these together, this says that our Dirichlet L function at psi to the power 4 times our amplifier squared, which is L squared. So this is basically at most P times L plus P to the 1 minus alpha times L to the A. So this implies that L of a half psi squared is at most P over L plus P to the 1 minus alpha L to the A minus 2. Oh, sorry, my 4 became a 2 for some unknown reason. And so this implies L of a half psi is bounded by P over L to the 1 over 4 plus P to the 1 minus alpha over 4 times L to the A minus 2 over 4. And the goal for this, for the amplification is to show L of a half psi is bounded by P to the quarter minus a little bit. Let's say beta. So this is the subconvexity problem. I have to imagine that probably some of the other talks have mentioned the subconvexity problem. Is that true?
Mentioned.
What's that?
It has been mentioned.
Okay. So so the convexity bound is P to the 1/4 here, and so beta. This is the subconvexity bound. I know that there were going to be some talks about like the delta method to proving subconvexity, and so this is part of the discussion of trying to use discuss the moment method for subconvexity. And so one of the approaches is to study an amplified moment. So for Dirichlet functions, the conductor is P, and so the convexity bound is P to the 1/4, and so we want to do better than that. So if you look at both of the two terms in this bound that we got, both of them are going to be okay. So the P over L to the 1/4 is okay for any, L is a small power of beta. So as long as you choose L to have some size, to be some small power of P, we're going to win on the diagonal term. So the amplifier helps us win on the diagonal term. So the amplifier helps us on the diagonal term. If we didn't have the amplifier there, we would get just P to the 1/4, and that's convexity. So L saves us on the diagonal. For the off diagonals, L makes things worse, but we're hypothesizing that we've already saved a power of P. So the P to the 1 minus alpha over 4 times L to the A minus 2 over 4 is okay for L equals P to the gamma some small gamma positive. Where how small it is depends on alpha and A and all this stuff. And so it's like a little complicated annoying optimization problem. But typically what you do is you just choose L to balance these two terms. So L will be some power of P. You can just do a little bit of algebra and solve for what you should choose for L on this and see what bound you get. But let's not worry too much about the particular exponents and how that plays out. The main thing is to see the idea and see how this should work. Great. So that's the method of amplification. It's been used in many, many problems, including some that you might not always expect. And it's just a really powerful idea. And so this is yes, I just wanted to mention the amplification as a yet another modified moment. So that's been the theme for the day. Are there any questions about that? Because I'm going to switch topics a little bit. Okay, so if not, then I wanted to talk more generally about families of L functions. So what's a family of L functions? It's a little bit hard to define precisely. There are a few papers on this in the literature, and they give slightly different definitions. But in practice, there are some examples of things that everyone agrees is a family, and so let's just define via examples. So one of the basic things that we're going to need as a basic input. So first of all, we need everything to be an actual L function. So we're having a collection of L functions. So need as a basic input, we need to be able to average over the family in some way. So we need to sum over elements in our family. So script F is our family of L functions, or maybe maybe a family of automorphic forms, like Dirichlet characters or something like that, giving rise to the L functions. And we need to be able to average over the Dirichlet series coefficients over the family. So suppose we have some collection of these L functions, and let's say we have some coefficients, lambda f of n, lambda f of n. We want to be able to average this over the family and do something with this. If we can't do this, if we can't get our hands on this, then we can't do anything. And we should expect that this is approximately the size of the family times some sort of delta function that m equals n. Although it's not always this, but so it could be, there could be a more general delta function here. So it could be more general. But often it's the delta function that m is equal to n plus some kind of error term. And this is as which is good as the size of the family goes off to infinity for m and n fixed. So let's give some examples. So the main example that we've worked with the past few days is if we have all Dirichlet characters mod q. And so that's our family, and then we're thinking of q as getting large. So something has to go off to infinity, and so the size of the family is the Euler phi function of q here, and so q is going off to infinity, and that means the size of the family is going off to infinity. So here the orthogonality formula, or the family average formula, is the orthogonality of characters. So that's some chi of m, chi bar of n. So this is phi of q times the delta function that m is congruent to n mod q. So it's not really saying that m and n are equal, but it's saying that they're congruent mod q. Okay, the screen went black for me. I don't know if you can see me or not. Okay, we're back. Okay, good. So that's our orthogonality formula that we've already been using. So another example would be the t aspect. So there, this is like if you integrate from minus t to t, m over n to the it dt, this is approximately 2t times the delta function that m equals n. Or more generally, it'll say that m and n are close, but if you just fix m and n and let t go off to infinity, then this is in the limit sort of telling us that m has to equal n. Another family that we could look at, we could look at, so we've got chi sub d, let's say, which is a primitive quadratic character, a primitive quadratic Dirichlet character. So you might just think about, so think of d as odd and square free. And then chi d would be the Jacobi symbol. So then you could look at averaging over these integers up to x. So d's means we're running over the primitive quadratic characters, which you might think of as just the odd square free integers. So we would need like m over d times n over d. And so this should be approximately the number of such integers, so some constant times x, if m times n is equal to a square and it's small. if m times n is not equal to a square. So here's a case where, okay, so if m equals n, then certainly the product is a square, but more generally, they don't have to be equal. M could be a square and n could be 1, and then you get a main term here. So when I was kind of lying, or I was oversimplifying it when I said that this is the delta function that m equals n. It's some sort of function that we can understand that certainly when m equals n gives us a main term, but there might be more main terms than that. But anyway, we call this our orthogonality formula for our family. So in this case, the orthogonality is sort of detecting that m times n is equal to a square. Okay, so these are all some degree 1 families or GL1 families. And it's very common to study also GL2 families. So here, let's look at SKQ. So remember, this was this is the vector space over the complex numbers of holomorphic modular forms. Of weight k on gamma 0 q. And this is a vector space, and it has an inner product, the Peterson inner product. So we can let's say b k of q. Oh, was there a question? Or we can let bk of q be a some collection, some orthonormal basis, or maybe orthogonal basis for SKQ. And we may choose BKQ to consist of eigenfunctions of all the Heck operators. T sub n. And okay, so the best we can really do in general is do this for all the n's that are co-prime to q. For the primes dividing q, it's more complicated than that. But Hecke showed that you can, there exists a basis, an orthogonal basis of consisting of these eigenfunctions of the Heck operators away from q. Okay, so then there's this Peterson formula. Which I'm not going to prove. It would take too long, and we'd run out of time. But for proof, you can see Ivanitz's book, Topics in Classical Automorphic Forms. And sorry. So what it says is that so there's some constant that depends on k that involves like gamma functions and powers of pi and all that stuff. But if you sum over these elements in this basis, and you take the coefficients, lambda f of m, lambda f of n bar, and then you divide by this inner product so that this thing scales appropriately, then this is equal to the delta function that m equals n. That's our sort of main term. And then plus some infinite sum. So it's 2 pi I to the minus k, sum over c congruent to 0 mod q. I don't know if other people have mentioned this Peterson formula this week, but it looks like this. So you have a sum of Klosterman sums, and then you have the k minus 1 Bessel function at 4 pi square root of mn over c. So the delta function is like you might think of as your main term, and then the sum of Klosterman sums is an error term. So for m and n fixed, you can show that the error term, like the sum of Klosterman sums part, so this part here is kind of relatively small. Although when M and N are large, it's very hard to prove that this thing is small. I mean, it's not always true that it's small, but anyhow. So okay, so this is our Peterson formula. This is our substitute. This is like our GL2 substitute for the orthogonality of characters. So this gives us a way to average over this family of these modular forms. And in this setup, there's a couple or a few different aspects. So you might let Q go off to infinity, where you hold the weight fixed. And we will call this the level aspect. We can also go the other way. So we could fix the level and let the weight go off to infinity. And this would be called the weight aspect. You can also sum over weights. Like K up to X, like some or in some interval or something like that. So you can also sum over the weights if you want to, and that will lead to better results. So this is our this is one of our well-studied families of so it's a family of modular forms, I suppose, but there's the associated L functions associated to these modular forms. And so we can study those L functions using this Peterson formula as a substitute for the orthogonality of characters. So all the techniques that I showed you today and yesterday for averaging over, try to understand moments of Dirichlet L functions, where we summed over chi, you could try to do the same thing where you sum over your family using the Peterson formula. And there are many, 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 many papers on this topic. Yeah. So there's a huge amount we could say, but let me just finish with just like a little bit. So maybe I'll just mention in passing, there's a variant of the Peterson formula called, or like a cousin of the Peterson formula called the Kuznetsov formula. And this is a version for Moss forms. So you can sum over Moss forms instead of holomorphic modular forms. And there's a similar type of formula, like structurally similar type of formula, although it's more complicated to write it down, and I don't want to write it down. So what else? So there is a, yeah, so there's a vast amount of work on moments of L functions in these families, and I have more I want to say about that, but maybe it's about time to stop, and we can just continue with this tomorrow, or Friday, I should say. So Friday, so this is a sneak preview. Friday, I'll talk about some moments with these GL2 families. Yeah, so I'm gonna stop here and let you go off and go home and do what you want to do, and I'll see you on Friday. So thanks.
You have any questions or comments?
Can you like explain a little bit about this the comment where you said like second moment will have long amplifier and fourth moment will have short amplifier?
So
Why?
so what I was getting at, or with that was so if I only had the second, okay, let's go up to where we were doing this. So if I only did this with the second moment, I would just get I would get like this. This would be like a P over L to the 1/2 plus this other correction factor. And to get the convexity bound back, L would have to be at least square root of P, just on the diagonal term alone. And so L would have to be quite big. So yeah, so L has to be bigger than square root of P. And so then also in this off diagonal term, I need to be a lot more careful about the powers of L that occur there. And so it was just, I don't know, it was kind of distracting, I think, from the main point. So usually we want to think of amplifiers as something that you use, like if you didn't have the amplifier, if like I studied this with L equals 1, maybe I could get like a diagonal term of size, it would be now P, and then a power saving error term like P to the 1 minus alpha. And the error term, it looks good. So if I took the fourth root, if I dropped all but one term and like just bounded an individual L function, the error term, the P to the 1 minus alpha part, would give me subconvexity, but the diagonal term is sort of ruining the day. So the diagonal term is too big. And it's just giving me P to the quarter, and there's nothing we can do about it. But the amplifier lets us win on the diagonal. So it helps on the diagonal, it makes things worse on the off diagonal. But in the second moment question, like I'm way off from the diagonal is like nowhere close to what I need it to be. So I would need I would need capital L to be quite large, and then the off diagonal is more complicated. So I just wanted to try to avoid that discussion. But you can read this paper by Friedlander and Ivanitz and see what they do. Does that answer your question?
Any more questions? If not, thanks, Matt, for wonderful lecture.
Okay, thank you.
Thanks, Matt, and see you on Friday.
Okay, happy Diwali.